It will be necessary to acquire a working knowledge of the air brake system. Every freight car is equipped with 5 basic air brake components: the brake pipe, control valve, auxiliary reservoir, emergency reservoir, and the brake cylinder with related rods, levers, rigging, and brake shoes. Let's explore the basic function of these components. The brake pipe may be considered the signal relayer. It is a continuous air line consisting of pipe and flexible hose. The brake pipe extends from the front of the train through each car to the rear of the train. It is closed at both ends during normal train operation, allowing pressurization. Brake pipe pressure is controlled through the operation of the automatic brake valve on the locomotive, except for some minor leakage in the system. The auxiliary reservoir is a storage tank charged from the brake pipe. This stored air pressure is delivered to the brake cylinder during service brake applications. The emergency reservoir is also a storage tank charged by the brake pipe. Air pressure from this reservoir is used primarily for emergency brake applications. A small portion of this air is also used during service releases to help recharge the system. The control valve consists of an emergency and service portion and is the signal receiver, the brain of the freight car. The control valve receives and interprets changes in brake pipe pressure and responds to apply or release brakes according to these pressure fluctuations. The brake cylinder, when pressurized, provides movement through a piston and a series of rods and levers to force the brake shoes against the wheel. This pressure provides the major retarding force necessary to slow or stop a train. The basic components are interconnected to one another through the control valve by piping. To better understand the control valve functions in applying or releasing brakes, let's look at some basic principles. Pressurized air stored on the locomotive moves through the brake valve into the unpressurized brake pipe. Given enough time, the entire brake pipe will attempt to charge to the pressure that is applied at the head end. The normal charging process may take up to 1 hour for a 115-car train. Pipe air pressure increases during this charging process. The auxiliary and emergency reservoirs on each car are also charged. Let's examine the freight car control valve operation, concentrating only on the auxiliary reservoir. By dissecting the control valve, examination of the internal parts can be made. The major component in the control valve is the service piston and related slide valve. The slide valve moves by applying air pressure to the service piston. Look what happens as the train is being charged. Since there is no air pressure in the auxiliary reservoir or the brake cylinder, the brakes are released. At each car, air diverts down the branch pipe. When the air pressure is sufficient to overcome friction of the moving parts, 1.5 pounds pressure is necessary. The piston and slide valve are forced to move. Notice when the piston moves, a port is uncovered, allowing brake pipe air to flow through a charging choke. Pascal's principle tells us that air will also flow into the auxiliary reservoir. Pressure will continue to build in the reservoir and on the back of the piston until equalized with the brake pipe. Once equalization is reached, the system is charged. The slide valve will remain stationary until there is sufficient air pressure change on either side of the piston to cause movement. To apply the train brakes, the engineer moves the automatic brake valve handle into the service zone. This allows brake pipe air to vent to atmosphere at a controlled rate. As a result, pressure throughout the brake pipe decreases, which also decreases the pressure on the left side of the service piston. When the pressure on the left side of the piston is 1.5 pounds lower than the right side, the higher pressure on the right side will cause the piston and slide valve to move from right to left. Watch as communication between the auxiliary reservoir and the brake cylinder is established. Air will flow from the higher pressure auxiliary reservoir into the zero pressure brake cylinder, forcing the piston to overcome spring tension and move outward. The movement of air from the auxiliary reservoir into the brake cylinder will continue until the pressure on the right side of the piston becomes slightly less than the left side. The greater pressure on the left side of the piston forces it to move to the right, terminating the connection between the auxiliary reservoir and the brake cylinder. This is called the lap position. While in the lap position, the auxiliary reservoir isn't permitted to charge any further. When the engineer decides it's time to release the brakes, he moves the automatic brake handle to the release position. This allows air to flow from the main reservoirs on the locomotive into the brake pipe, increasing the pressure in the brake pipe. Looking once more at the control valve operation, as brake pipe pressure increases throughout the train, pressure is also building on the left side of the piston. Once the pressure on the left side of the piston becomes 1.5 pounds greater than the right side, the piston moves. This movement of piston and slide valve accomplishes two things. First, a port in the slide valve allows air trapped in the brake cylinder to escape to atmosphere and release the brakes. Secondly, brake pipe air is allowed to flow through the charging choke to the right side of the service piston. This air is used to replenish air in the auxiliary reservoir that was used during the previous brake application. The brakes are now released, the system recharged, and a complete application and release cycle of the brakes has been observed. Up to this point, this study has been confined to service brake applications. This involves the service portion of the control valve, the auxiliary reservoir, and the brake cylinder.